first derivative test, intervals of increasing and decreasing. So we got some rational functions right here. And let's just jump into it. We know we're going to have to take the first derivative, and I'm going to use my quotient rule. I'm going to go low d high, and I'm going to see that negative as being with the x on top. So derivative of negative x times my low d high minus high d low, all over low. Now, you don't have to simplify this, but I'm going to simplify this. I think it's going to make my life easier as I finish this problem. So I'm going to distribute that -1 to get negative x squared plus 1 plus, that'd be a plus 2x squared. And combine like terms here. I've got, denominator is still an x squared minus 1 squared. And when I combine like terms on the top, I do have x squared plus 1 all over x squared minus 1 squared. All right, now once we take our first derivative, and notice when it's simplified, that it's going to be pretty easy to work with compared to that right there in red. So once I do have my first derivative, we're looking for critical values. Remember, critical values are when that first derivative doesn't exist or when that first derivative equals 0. Because we have a rational function, a fraction, essentially, is our function right here. A function equals 0 when the numerator equals 0. Well, notice x squared plus 1 will never equal 0. So there are no critical values for when our first derivative equals 0. But we do have some critical values for when the first derivative doesn't exist. When do we get division by 0? At x equals positive and -1. We would get division by 0. So those are our critical values. I'm going to slap those critical values on my number line, thinking about the intervals to the left, to the right, and in between. And of course, what is going on those actual intervals? What is my function doing? And in order to know what my function is doing, I'm going to use my first derivative. So, really negative values, more negative than -1. If we plug them in right here, no matter what we do, notice this, no matter what we plug into the top, we're going to get a positive number. And no matter what we plug into the bottom, unless it gives us 0, when we square it, it's going to be a positive number. So we already know, and notice this, we're really kind of summarizing a lot of the next steps of this problem. The numerator is always positive. The denominator is either 0 or positive. We know when the denominator was 0, so that must mean that in every one of these intervals, no matter what we plug in, it's going to get us a positive value for our first derivative. So my first derivative is positive on this interval. My first derivative is positive on this interval. My first derivative is positive on this interval. That means it is increasing from -infinity to -1. It is increasing, it's increasing, and I'm just going to write it like this. It's increasing right here from -infinity to -1. It's increasing from -1 to 1. It's increasing from 1 to infinity. On all three of these intervals, it is increasing. On all three of them. And so think about the first derivative test, right? We checked those critical values. And it never did change from increasing to decreasing. right there is already telling us we don't have any relative extrema because it never did change from increasing to decreasing or vice versa. There are no intervals of decreasing. But on top of that, at -1, if you plug that into the original function, at -1, that point does not exist. If we plug in +1, that point does not exist. So even if it did change from increasing to decreasing on these intervals, because a -1 and +1 are not giving us actual points on the actual function, then they would not be relative extrema. So for multiple reasons, there are no relative extrema, and we do have 3 intervals of increasing. Let's see it on a graph. Let's visualize it. Okay, clearing it off. I hate clearing it off because then what if we need it? What if we need it? It's just, you can't do it all. All right, here, let's try this. Oh goodness. Okay. Ah, there we go. We can type it in easier. All right, we can type in a fraction if you like. Here is a shortcut, alpha. If you go alpha y equals, that is pulling up the F1. And notice number 1 on F1 is numerator divided by denominator. Let's choose that shortcut to getting that fraction in there. I want a negative x over x squared minus 1. Oh, why did it do that? All right. Calculating calculators. Let's try this again. All right, x squared minus 1. That's it. That's the function. Let's graph it. Let's zoom 6 this bad guy. Whew. There it is. Check it out. At -1, at +1, there were infinite discontinuities. We saw that was giving us division by 0 in that original function. There's our original function that would give us -1 and +1 divided by 0. Yes, that makes sense. It would be an infinite discontinuity. And it's increasing, it's increasing, it's increasing on all 3 of those intervals. Wowee. All right, going back, let's look at this second rational function. What does this one have for us? Let's find out. And so, of course, we're going to jump right into our first derivative, and I'm going to, all right, we've already talked about this one. I'm taking the first derivative, I'm applying it right here above. I'm going to once again use my quotient rule. So low d high minus high d low all over low low. You know I'm going to simplify this. 6x squared minus 6x minus 3x squared when we combine like terms on the top, we have 3x squared minus 6x all over 3x minus 3 squared. And I believe I can, well, just for my own happiness, I'm going to factor out a 3x on the top, leaving me with x minus 2. So nothing cancels out, but it's kind of nice to see the numerator and the denominator factored. It's nice for me. Maybe it's nice for you too. But now we need to look for critical values. When do we have critical values? When the first derivative equals 0 and the first derivative does not exist. And the first derivative here will do both of those things. The first derivative does not exist when the denominator equals 0. And when will the denominator equal 0? When x equals a positive 1. And we also have critical numbers when our overall first derivative equals 0, and that would be when the numerator equals 0. When will the numerator equal 0? When x equals 0 and when x equals 2. So there we go. We've got 3 critical numbers. Let's throw them down on our number line. Boom, boom, 3 critical numbers. We need plenty of space, but at least they're nice, simple numbers. What a blessing. 0, 1. Not very spaced out. Yeah, okay, I'll be fine. 0, 1, and 2. I did the big number line. I got excited with big gaps, and then you run out of space. What you going to do? All right, we got our intervals. Negative infinity to 0, 0 to 1, 1 to 2, and 2 to infinity. Of course, we want to know what is our first derivative doing around here. If our first derivative is positive, then we know our original function is increasing. Our first derivative is negative. We know our original function is decreasing. So right here, negative values, what are they doing to our first derivative? Looking at really negative values. Well, the denominator is always going to be positive because the whole thing's being squared. It's always going to be positive except for that one value where it's 0. So it's really the top that we have to worry about. The bottom's always positive. The top, it would be a negative times a negative. No matter what you plug in right here, as long as it's really a negative times a negative, which will overall give us a positive for our first derivative. And because our first derivative is positive, we know y is increasing on this interval from negative infinity to 0. Now from 0 to 1, this one might be a little trickier because it is, there's no whole numbers right there, but think about a half, sure. We know the denominator actually, the denominator is positive. Remember, the denominator is positive, but the top, think a half times 3 is positive. Half minus 2 is negative, so the numerator is negative. It would be a positive times a negative. So we have a first derivative that is negative. So that means our original function is decreasing on this interval. And finally, from 1 to 2, well, not finally, I still have 2 more, but 1 to 2 is going to be very similar as from 0 to 1, because from 1 to 2, denominator is positive. It's a positive. Something less than 2 minus 2 is still negative. A positive times a negative is still a negative. So that means our original function is still decreasing right here on the interval from 1 to 2. Now finally, from 2 to infinity, really positive numbers times 3, really positive numbers minus 2 are all positive. And so our original function is increasing on this interval from 2 to infinity. Whew. So we do have a change in direction here. We do have a change in direction here, right here. We did not have a change of direction. Decreasing to decreasing. And I'm already talking about changes of direction. I'm applying that first derivative test. And if we change direction if we don't change direction, we have no relative minimums and maximums. But again, it would not have mattered because at 1, our original function doesn't exist. And in order to have a relative extrema, that point has to exist. So we have no relative extrema right here at 1, but at 0, it exists in the original function. It changed from increasing to decreasing. Y changed. Y changes. Changes from increasing to decreasing. So what do we have? We have a relative maximum. And it is at the point where x is 0. Plug that 0 back into the original function and we get 0. There's a relative maximum at 0, 0. At 2, what's going on? Well, it goes from decreasing to increasing. Y changes from decreasing to increasing. So we're going to have a relative minimum when x is 2. Plug that 2 back in the original function. That would be 4 over 2 times 3 is 6. Minus 3 is 3. 4/3. Let's see it on a graph. All right, let's see it. Let's see it. It's gone. Okay. All that work down the can. All right. Shortcut to our fraction. On the top, we've got x squared. On the bottom, we have 3x minus 3. And let's see it. Zoom 6, that bad guy. Whoa. All right, notice we do have a relative minimum. It does seem to confirm our 0, 0 is what we said our relative minimum was, because it went from increasing to decreasing. Right here at the x value of 1, we have an infinite discontinuity. Decreasing to decreasing on either side of 1. And then right here at, it looks like 2, well, that's what we said with our calculus and our algebra. We said 2, where it changes from decreasing to increasing. So I'm just going to double check that right there. I'm going to calculate that minimum. Okay, there we go. All right, left bound, inner. Right bound, inner. Let's guess. All right, notice it says 2.0000145. 4/3! Okay, so it's getting really close to that 2 against a calculator. Give it a break. It's not as smart as we are. It's doing a lot of limits behind the scenes. So it got 4/3. I mean, that's nice. All right, there it is.